And Fred, always good to see you. So Fred, how do you feel and what is your takeaway today?
Thank you. And I think you should have received the book through PDF.
Oh,
Yes.
I received the Living Energies. It's just that I also bought the physical copies, you know. Also, I
Yeah,
can
yeah.
get. Okay, okay.
But
Hey guys,
did you
I
receive
I I
the Programming the Universe via email?
Okay, I'll look for it. I'll look for it.
everybody should have got it, and I added a couple things that were left out of the PDF file. I added a couple things in that were in the book that were not in the PDF file. So, and then I'm
Yes.
going back into my thing, and I'll be joining you in about 20 minutes. Good. Okay, cool.
Thank you very much.
Thank you, Stephen. Manu, how are you feeling and what is your desired takeaway?
Oh, I'm caught unawares here. Anyway, I'm just emerging out of from a bad flu, and I just hope that I'm going to be able to hold on and to participate to the fullest. And I'm grateful to be here. So, who's next? Oh, okay, Fred. How do you feel? What's the expectation?
Thank you, Manu. I look like I feel better than you. Did you catch a cold or something? Or did you just fall out of bed or I don't know. You look like you could use a rum in your coffee. Yeah. Yeah. How am I feeling? Yeah, I'm feeling pretty good. My little dog was sick, but so she spent 3 days in hospital. She's back yesterday. She looks okay, but she's still a little bit lacking some energy, under the weather. But hopefully she'll be fine. And I'm very excited to start a new book. I've received the amended copy by Steve, and I did not like his amendments, so I redid the amendments to add pages. So I will, after the call, I will send again the final copy of the book, so I will probably add page numbers on the table of contents because it might be useful to have that, and then we will be able to use the same PDF copy, so the page numbers will coincide when we say that's the page we are in. So we'll do that. And other than that, let's try to learn a little bit something and start reading the book, if you all agree. So the recording has been started. Steve will be joining us in maybe 15 minutes. He has some family event that he has to attend, but he'll be back soon and he will join us for the call. So I'm going to share my copy of the book and then we can start reading if you all agree.
Yeah. All good.
Let's try to set an example for Wednesday call where they just run around in circles before getting to work. Okay, can you all see the screen sharing?
Yes,
Okay.
very clear.
Good. Now I need to do this. Okay, so we're starting Seth Lloyd's Programming the Universe, 2006 book. I'm going to read the addition that Steve has put on. So Seth Lloyd, Programming the Universe. Seth Lloyd is a professor of mechanical engineering at MIT. MIT is Massachusetts Institute of Technology in the US. He's a principal investigator at the Research Lab of Electronics, and he's the designer for the first feasible quantum computer. He has been featured in the New York Times, the Los Angeles Times, the Washington Post, The Economist, and Wired, amongst other publications. His name frequently appears as both a writer and a subject in the pages of Nature's New Scientist, Science and Scientific American. He lives in Cambridge, Massachusetts, and he can be joined via his website at cesloids.com. Then there's an acclaim for his book. Do we want to read that? I think we can all read it on ourselves. Let's get started with the book itself. So I put a table of content on one page, and we've got 2 parts in this book and 8 chapters to go through. It's around 200 something pages. Where can I see the pages? 277 pages. This book is dedicated to Eve. I don't know who Eve is, but probably she's important to Seth Lloyd. Prologue, the apple and the universe. In the beginning was the bit, I began. The chapel in the 17th century convent that housed the Santa Fe Institute for the Study of Complex Systems was filled with the usual collections of physicists, biologists, economists, and mathematicians, with a leavening of Nobel laureates. The grand old man of astrophysics and quantum gravity, John Archibald Wheeler, had challenged me to give a talk on the subject, it from bit. I had accepted the challenge. I was beginning to wonder if that had been a good idea, but it was too late to back down now. I held an apple in my hand. Richard, welcome to the call. We just started reading the prologue of the book. How are you feeling, and what is your desired takeaway for today?
I'm feeling a little bit behind. My computer was slow in getting started, and I'm looking forward to getting into this new book, and I've continued to have some progress in my meetings with the possibilities of a new director of Perry Center coming to the University of Calgary. So that's a positive. We had a nice meeting yesterday. So I'm really looking forward to getting into this whole question of programming the universe. So I expect to get a good introduction into that this evening. Thank you.
Wonderful. We just started, so you missed nothing. Even you feel behind, you're not. You missed Anne's and Manu's introduction, and my introduction, which is really pity. But as far as the reading is concerned, you have missed nothing. We were just at the first paragraph. Where is it? Here. No, I'm sharing the wrong thing. So I'm going to share again. So we were just at the first paragraph of the book, and Seth Lloyd was explaining that he was at the Santa Fe Institute of Technology, who specializes in complexity, in the study of complexity, and he had accepted a talk to discuss about it from bit, and that was the first paragraph of it. Sorry, I'm trying to figure out how to set on the screen. So you see, okay, now you can see what's the first page of the book. Okay, I keep going on the second paragraph, just here. If you can see, yes, you can see. Okay, things or its arise out of information or bits. I continued, nervously tossing the apple in the air. This apple is as good as it. This apple is a good it. Apples have long been associated with information. First of all, the apple is a fruit of knowledge, whose mortal taste brought death into the world, and all are whose. It conveys information about good and evil. Down the line, it was in the trajectory of a falling apple that Newton traced the universal laws of gravitation. And the curved surface of the apple is a metaphor for Einstein's curved space-time. More directly, the genetic code locked in the seeds of an apple programs the structure of future apple trees. And last but not least, an apple contains free energy, the calories of bit-rich energy that our bodies need to function. I took a bite of the apple. Any comments at this moment?
Sure that isn't a bit of the apple?
I took a bite of the apple. Did I say a bit of the apple? I'm already contaminated by it from bit.
No, that was my
Thank you.
contamination.
Thank you for the connection, for the correction, Richard, or for the pun. I think that was a pun. I think you did it on purpose. Clearly, I'm sorry.
Yeah, I just wanted to make a comment.
Sure. Yes, go ahead.
Okay. Is he saying that happenings are quanta of information?
Can you repeat the question?
Is he saying that happenings, the whatever we call anything that we identify, are finite quanta of information?
I don't think it says that yet. Maybe it will later. At this moment, it says it are things. It is a physical world that is issued from bits, which is the information world.
I say that because you say the apple contains a finite amount of energy to make that apple or something, and had a bite at the apple. So a thing is, actual fact, a finite amount of something that is information that presents itself in a form.
Maybe.
We'll see.
Maybe that's what he means. We'll see. Good remark. Thank you. Clearly, there are many types of information contained in this apple, but how much information does the apple embody? How many bits are there in an apple? I placed the apple on the table and turned to the board to perform a short calculation. Interestingly, the number of bits in an apple has been known since the beginning of the 20th century. Since before the word bit, at first, one might think that an apple embodies an infinite number of bits, but this is not so. In fact, the laws of quantum mechanics, which govern all physical systems, make finite the number of bits required to specify the microscopic state of the apple and its atoms. Each atom, by its position and velocity, registers only a few bits. Each nuclear spin in an atom core registers but a single bit. As a result, the apple contains only a few times more bits than atoms, a few million, billion zeros and ones. I turned back to face the audience. The apple was gone. Not good. Who had taken it? I glanced at the benign face of Wheeler and the impassive expression of Murray Gell-Mann, Nobel laureate, inventor of the quark and wearer of one of the world's physics heavyweight title belt. I can't continue without the apple. No it, no bit, I declared, and sat down. The hunger strike lasted only a few moments before an impish engineer from Bell Labs produced the apple. I took it from him and held it on high, issuing a challenge to anyone who might attempt another theft. This was a mistake. For the moment, though, all seemed well, I continued. All bits are equal in terms of the amount of information they can register. A bit, short for binary digit, is registered by two distinguishable states, 0 or 1, yes or no, heads or tails. Any physical system with two such states registers exactly one bit. A system with more states registers more bits. A system with 4 states, for example, 0, 0, 0, 1, 1, 0, 1, 1, registers 2 bits. A system with 8 states, for example, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, registers 3 bits, and so on. As I mentioned before, quantum mechanics guaranteed that any physical systems with finite energy confined to a finite volume of space has a finite number of distinguishable states, and therefore will register a finite number of bits. All physical systems register information. In the words of IBM's Rolf Landauer, information is physical. I think this is very important. I think this is very important that quantum mechanics guarantees that any physical system with finite energy confined to a finite volume of space has a finite number of distinguishable states, and therefore will register a finite number of bits. I will see if I can put some color on that. Annotate. No, it did not work. Quantum mechanics guarantee finite number of bits, and if I do this, now it worked. Somebody's got his hand up. Manu, go ahead, please.
I agree with you that this is extremely important.
Thank you.
Let me try to put it in the lay term that I think I understand. It says everything is an aggregate of things, of finite things. And everything is or is not. You could say is visible or non-visible. There is a spin to it. So if it is or is not exclusively, the description of any aggregation of things would be made of bits that are a succession of is not, etc. So 0, 0, 1, 0, 0, 1, etc., etc. And that aggregation will make the whatever it is, that is the thing and the information. Does it make sense, Fred?
It does. It does. Does it make sense for everyone? Okay. I think at this stage in the book, things don't have to be fully clear in order to continue, because it's the introduction. So we will get back to this concept. So it's I think it's okay to keep going. We're in agreement. So let me share again my book. Here and my screen. There we go. We're here. No, bad idea. Here, Gell-Mann interrupted. But are all bits truly equal? What about the bit that tells us whether some famous and solved mathematical conjecture is true or not? Compare that with a bit derived from a random coin toss. Some bits are more important than others. True, I agree. Different bits play different roles in the universe. All bits can register the same amount of information, but the quality and importance of that information varies from bit to bit. The significance of yes depends on the question asked. The 2 bits of information that determine the identity of a base pair in the apple's DNA are far more important for generations in the future for generations of future apples than the bits of information registered by the thermal jiggling of a carbon atom in one of the apple's molecules. Only a few molecules and their attendant bits are required to convey the smell of the apple, whereas billions of bits are needed to provide this apple with its nutritional value. But, Genman interjected, is there a mathematically precise way of quantifying the significance of a bit? I did not have a complete answer to this question. I replied, still holding the apple. The significance of a bit of information depends on how that information is processed. All physical systems register information, and when they evolve dynamically in time, they transform and process that information. If an electron here registers a 0 and an electron there registers a 1, then when the electron goes from here to there, it flips its bit. The meaning is that it changes from 0 to 1 or from 1 to 0. It flips its bit. The natural dynamic of a physical system can be thought of as a computation in which a bit not only registers a 0 or 1, but acts as an instruction. 0 can mean do this and 1 can mean do that. The significance of a bit depends not just on its value, but on how that value affects other bits over time, as part of the continued information processing that makes up the dynamical evolution of the universe. Joe, welcome aboard. Would you like to tell us how you feel today and what is your desired takeaway?
Sure. I'm feeling pretty good. It's been a good day here in Philadelphia. So there's a lot of celebrating going on outside, even though I'm not even in New York. But because the New York basketball team won the championship. So, no, it's I'm really looking forward to actually going through this book, and even just looking at the one page that we were going through a moment ago is you could see a lot of information theory that is actually going to be relevant in our discussion, which I think is actually a very important way of thinking about all of our interactions. So anyway, looking forward to going through the book, and it's good to see everybody.
Thank you very much, Joe. Okay, Joe, we've talked about, we started the book. We're on page, I think, 2 of the introduction of the, page 3, 4 of the prologue. I'm going to share again so you can get acquainted with what we've said. It's a prologue, so there are a few concepts that are given, but they're given as an example, and we'll have a lot of time to dive deeper into those concepts as we go through the book. So what we've seen is that most important things is that every thing can be described by a limited number of bits, a finite number of bits. Then we saw that quantum mechanics guarantees that any physical system with finite energy confined to a finite volume of space has a finite number of distinguishable states and therefore will register a finite number of bits. Then we just saw that some bits are more important than others, and that the significance of a bit depends not just on its value, but on how that value affects other bits over time. And I think that brings you back up to pace with all of us.
Yeah, so it's basically getting into the idea of cause and effect.
Mm-hmm.
I am not sure about that. He did not mention that.
Because the significance of a bit depends not just on its value, but on its how it value affects other bits over time. So over periods of time, how's each bit impacting the next one? And that's the data inputs, if you think about it, in even our behaviors.
Okay. I take your remarks. I'm not saying it's not correct. I'm saying I don't know if that's what it means. You probably know better than I do on that cause and effect situation. So thank you. Good remark. Shall we keep going?
Can I comment?
Yeah, sure.
Okay. It looks to me that the significance of a bit depends, loosely on questions like bias and local conditions. If I want to preserve the apple for a certain time, the value of information is a certain bias for that to be consistent over that period of time. So it is the bias from what is desired at the local. Because overall, it is 1010 binary all over. 101010 infinitum. But if I want to do something like the guy say he can't do anything without his apple, that apple has a specific bias of bits at those local conditions. And if you want to preserve those for a certain amount of time, those bits will have to take certain bias values. Let's just put it value. I'm putting value.
Are you saying bias, B-I-A-S?
Yes, bias. Yes.
Okay.
Is a proclivity.
Okay. I'm not sure I understand bias in this context, but thank you for precision.
Yeah.
What
I mean by bias is proclivity. Yes.
Yes, I understand proclivity and I understand bias, but not in this context.
Okay.
Are you trying to say that the importance of a bit depends on what for?
Yes, on the local conditions, yes, that you want to preserve.
Okay. Okay. Thank you.
So information is only information as we value it locally.
Okay, I understand now. Thank you. Anybody else?
Yeah, I like to share something. I just went to pull out the cosmometry book because ever since this was like in the prologue of the whole book, right? Introduction to cosmometry. I used to, from the very beginning, I was very, very puzzled by this energy, matter, and information. Even reading through the whole book, I couldn't connect the fact that the whole universe. It's information as well, right? But today, because of this programming the universe, suddenly it comes in and it starts to connect. Make sense of what they mean by information. Because whatever is all around us is information, So there was one thing I couldn't link and couldn't, for the life of me, make any sense of. But I'm just so happy that the first chapter itself connected the previous book to this book. Thank you. Just a comment.
Yes. Thanks for that. And yeah, The trend in the last 30 years has been to, I was going to say reduce, it's not reduce, but explain everything in physics and everything else in terms of information theory. And basically, information theory has gained preeminence over all other descriptive sciences. And everything in those sciences can be explained in terms of information theory. The big problem everybody has is that in a normal science curriculum, nobody has heard a lot about information theory. We don't know. We don't have the basics to understand it and to see things in terms of information theory. That's where this book is going to help us a lot in this regard. Anybody else? No. Share again. Oh, there's stuff in the chat. Thanks for the explanation in the chat, Manu. Okay. I continued to identify the bits from which the apple arises and to elaborate the roles those bits play in the processes that make up the apple's characteristics. Let me repeat that again. It's a mouthful, this sentence. I continued to identify the bits from which the apple arises and to elaborate the role those bits play in the processes that make up the apple's characteristics. Things were going well. I had addressed the problem of it from bit, and I had survived the questioning, or so I thought. As I finished the talk and stepped away from the board, someone tackled me from behind. One of the audience members had taken seriously my challenge to steal the apple. Doyne Farmer was one of the founders of chaos theory, a tall, athletic man. He grabbed my arms to make me drop the apple. To break his grasp, I slammed him back against the wall. Pictures of fractals and photos of pueblos fell, but before I could wriggle free, Farmers wrestled me to the ground. We rolled around the floor, overturning chairs. By now the apple was gone. It had been reduced to bits. Okay. All right. We're done with the introduction. The prologue, actually, was it prologue or introduction? The prologue, we're done with that.
I like the way it ends that, because we always know that at the border of a finite, there are always events that will affect you. And that comes, and then the apple was no more. It was reduced to bits again. It's something that happened, and that took him unawares. He wasn't prepared for that. He thought that he had arranged the understanding of what the apple was, and extra. But at the end, that scene where they have that little simulacre fight,
yes,
and the apple goes to bit, it says what it is.
Yes.
That's where nature is.
Agreed. The book is pleasantly written. It's very pleasantly written. We're going to discover that together, but I enjoyed reading it many years ago. Steve,
And that is
yes, go ahead.
Yeah.
Manu.
That's the definition of finite. When you say universe is finite, that's what it means.
Yes.
Because universe is the order of understanding of things. What is accepted by us, and version, universe, is what we accept. But when catastrophic events happen, that understanding is shattered. And so universe is dynamic. Our understanding must evolve if we survive.
Yes, I agree with you. There's actually another way to etymologically understand universe. Verse is what the plow makes when you go from one end of the field to the next, to the other end of the field. And it's also in poetry, a verse, or in the Bible, it's one line of text. Universe means unique line of text, but when you want to plow a field or write poetry, you write other lines of text and other lines of text. And somehow, this etymological interpretation goes either in the sense of multiverse, one of the interpretation of quantum theory, or the fact that there may be more than one track of universe.
Yes. Yes.
That's anyway. That's the etymology of universe I looked up from previous calls. I had Steve with his hands up, and then he disappeared. So let's keep going. We're going to part one, the big picture, and I need to share my book again. It's a lot easier when somebody shares the book, and it's not the reader that has to do all the work. Hey, Steve is back. Anne is very patient. Manu and Richard just disappeared.
How long has this thing been down?
Ever since you shut your phone down, you shut us all down. You did not make me a co-host.
I fell into a pocket, and my phone wouldn't reboot. Totally crazy.
Yeah.
I
So that's
apologize.
it's been 25 minutes, maybe?
Oh, geez. I'm so sorry. So I'm going to go back on mute for a little bit, and then if you can recover, it was a good meeting. I listened to a lot of it as I was driving.
If you know what? If you make me a co-host, this will not happen.
I thought I made you the co-host.
No, I was not.
You know what? Maybe I didn't. I thought I did, and I think you're right. If I'd done that, oh my gosh, I'm so very sorry.
Yeah, it's okay.
Okay.
It's okay.
Yeah,
Don't worry too much about it. That's what's done is done. We still have we still have 1 hour to go, so let's do that. If you make me a co-host now, which I don't know how you can do that, I'm trying to figure it out. Then it won't happen.
I thought I'd made you co-host, Fred, and I totally apologize. My total screw up. You did such a good job getting the meeting going on time. Thank you.
Yeah, we started just Anne and I on time.
Don't worry about it, Steve. All good, all good. Things happen.
I love this book.
It's I think we made a good choice. That's a good book, and it's well written.
And we're just at the prologue,
Already Anne made some connections with previous something tracks. So the light turned on, which is really good. I think Richard, where's Richard? Manu, where's Manu? Come on. Manu went back to bed. And Richard, I don't know. Oh, there's Richard.
I'll text.
Sorry for the mishap, Richard. I was not made a co-host, and when Steve inadvertently got disconnected, then the meeting shut down on us. I think we should give Manu a chance to rejoin. Hopefully he did not go back to sleep.
I will take complete responsibility for not consciously pushing the button to make Fred a co-host. When my phone died, I thought, well, there's no problem. Fred's a co-host. And I realized I didn't do that. I apologize.
What do you mean exactly? You're going to send us a check or something?
Yeah.
All right, let's get going. Everybody, we lost Joe. We lost Joe. So we are in part one. We're about to start part one, the big picture, chapter one, introduction, and I'm going to share my book, which is when Steve disappeared last time. There we go, the meeting, my screen. Okay, oh, no. There we go. No, not this one. Sorry, I'm messing up with my windows. There we go. Good. We start here. Okay. Chapter one, introduction. This book is the story of the universe and the bit. The universe is the biggest thing there is, and the bit is the smallest possible chunk of information. The universe is made of bits. Every molecule, atom, and elementary particle registers bits of information. Every interaction between those pieces of the universe processes that information by altering those bits. That is, the universe computes, and because the universe is governed by the laws of quantum mechanics, it computes in an intrinsically quantum mechanical fashion. Its bits are quantum bits. The history of the universe is, in effect, a huge and ongoing quantum computation. The universe is a quantum computer. Any comments on that?
Information
This begs the
flows.
que-
It always flows.
Yes, thank you for that, Manu. Anything else? This begs the question, what does the universe compute? It computes itself. The universe computes its own behavior. As soon as the universe began, it began computing. At first, the patterns it produced were simple, comprising elementary particles and establishing the fundamental laws of physics. In time, as it processed more and more information, the universe spun out ever more intricate and complex patterns, including galaxies, stars, and planets. Life, language, human beings, society, culture, all owe their existence to the intrinsic ability of matter and energy to process information. The computational capability of the universe explains one of the great mysteries of nature, how complex systems such as living creatures can arise from fundamentally simple physical laws. These laws allow us to predict the future, but only as a matter of probability, and only on a large scale. The quantum computational nature of the universe dictates that the details of the future are intrinsically unpredictable. They can be computed only by a computer the size of the universe itself. Otherwise, the only way to discover the future is to wait and see what happens. Any comments? I see Manu agreeing with all that. All right. Allow me to introduce myself. Yes, please.
Well, I mean it seems pretty profound to underscore the lack of predictability, and when you put that in the context of science, it seems to, if you want, argue or is in favor of predictability. And that may be attributed to what might be considered, what I consider anyway, old pre-20th century science. And if it's correct around what the quantum is all about, reality, that there is no predictability, it seems that the old notion of the physical sciences and measurement are outdated, and yet here we are a century and a quarter beyond that outdating, and we're still governed by that notion of predictability. I don't know if
Thank
that
you,
makes
Richard.
any sense, but
No, it does. In this context, it does make a lot of sense. There's I'm in no way a specialist in anything quantum, but I am looking into it. And somehow I'm confused about this predictability nature of the universe. Because one of the things I've looked at recently was saying that quantum physics was inherently able to predict the future. But I don't understand that assertion. So this is really something that we may discover or we may get more information about, either reading this book or through personal research. But I agree with you. This the way it's formulated here, it's a complete contradistinction, to use Bucky's words, to the pre-20th century science and the way of describing the universe, including Newton and even Einstein's formulation of the laws of physics is inherently predictable. Manu, please go ahead.
Yeah, it's interesting that Richard talks about predictability, not prediction. Predictability is very consistent with probabilities. In that, and the principle that we can only make sense of anything as you repeat, and then we see the likelihood of it. But we cannot say for sure 100% or 125% is going to be. That's prediction. But by all means, being inside the universe, we'll always try to tessellate to the best that we can. And that can only tend towards, so give a probability towards something, without ever saying that that is exactly that thing that's going to happen. So our future is just expansion within the container.
Yeah. Well, that doesn't change my observation that we and the royal we seem to be a century and a quarter behind the issue of prediction and predictability, if it's really probability and not predictability.
But I'm saying there's a profound difference between prediction and predictability. It's
Yeah,
profound.
I know you are, but do you also agree that the old science, the pre-20th century science, still dominates and controls and asserts the principle, if you want, or the measurement of prediction?
Oh yes, I mean that's politics. We all know that anybody that says, everything is definite and precise is playing politics, is not playing science.
And yet here we are, a century and a quarter, and it hasn't been taken up in a paradigm shift or transition. Interesting.
Yeah.
Anyway, it's just an observation and a feeling that I have, trying to make sure that I'm not in a mistaken sort of judgment about where we are in the evolution of our sciences.
Yeah, thank you for that, Richard. Manu, anything more? Okay, Anne? Okay. We're here. Allow me to introduce myself. The first thing I remember is living in a chicken house. My father was apprenticed to a furniture maker in Lincoln, Massachusetts, and the chicken house was in back of her barn. My father turned the place into a two-room apartment. The space where the chicken had roosted became bunks for my older brother and me. My younger brother was allowed a cradle. At night, my mother would sing to us, tuck us in, and close the wooden doors to the roosts, leaving us to lie snug and stare out the windows at the outside, at the world outside. Stare out the windows at the world outside. My first memory is of seeing a fire leap up in a wire trash basket. My first memory is of seeing a fire leap up in a wire trash basket with an overlapping diamond pattern. Then I remember holding tight to my mother's blue jeaned leg just above the knee, and my father flying a Japanese fighter kite. After that, memories crowd on thick and fast. Each living being's perception of the world is unique and crowded with details and structure. Yet, we all inhabit the same space and are governed by the same physical laws. In school, I learned that the physical laws governing the universe are surprisingly simple. How could it be, I wondered, that the intricacy and complexity I saw outside my bedroom window was the result of these simple physical laws? I decided to study this question and spent years learning about the laws of nature. Heinz Pagels, who died tragically in a mountaineering accident in Colorado in the summer of 1988, was a brilliant and unconventional thinker who believed in transgressing the conventional boundaries of science. He encouraged me to develop physically precise techniques for characterizing and measuring complexity. Later, under the guidance of Murray Gell-Mann at Caltech, I learned how the laws of quantum mechanics and elementary particle physics effectively program the universe, planting the seeds of complexity. These days, I am a professor of mechanical engineering at the Massachusetts Institute of Technology, or because I have no formal training in mechanical engineering, I might be more accurate to call me a professor of quantum mechanical engineering. Quantum mechanics is a branch of physics that deals with matter and energy at its smallest scales. Quantum mechanics is to atoms what classical mechanics is to engines. In essence, I engineer atoms. In 1993, I discovered a way to build a quantum computer. Quantum computers are devices that harness the information processing ability of individual atoms, photons, and other elementary particles. They compute in ways that classical computers, such as a Macintosh or an IBM PC, cannot. In the process of learning how to make atoms and molecules, the smallest species of the universe, compute, I grew to appreciate the intrinsic information processing ability of the universe as a whole. The complex world we see around us is a manifestation of the universe's underlying quantum computation. The digital revolution underway today is merely the latest in a long line of information processing revolutions stretching back through the development of language, the evolution of sex, and the creation of life to the beginning of the universe itself. Each revolution has laid the groundwork for the next, and all information processing revolutions since the Big Bang stem from the intrinsic information processing ability of the universe. The computational universe necessarily generates complexity. Life, sex, the brain, and human civilization did not come about by mere accident. Any question?
I think I have something to say, because as we were reading these last few paragraphs here, this suddenly reminds me of music. In cosmometry. I'm sorry, I keep going back to cosmometry, right? Because it said that music was not created by man, right? It exists, it's there. So that means information is not created by man either, because it exists out there. Just we learn how to capture that information. Would I be correct in saying that then? Yeah, I'm done with that part. It just occurred to me, that then it exists. We didn't make it, we didn't create it, yeah. Just like music. I'm done.
Okay, thank you. Thank you, Anne. Anybody else? All right. We start here now. The quantum computer. Quantum mechanics is famously weird. Quantum mechanics is famously strange. Waves act like particles, and particles act like waves. Things can be in two places at once. It is perhaps not surprising that at small scales, things behave in strange and counterintuitive ways. After all, our intuitions have developed for dealing with objects much larger than individual atoms. Quantum weirdness is still disconcerting. Niels Bohr, the father of quantum mechanics, once said that anyone who thinks he can contemplate quantum mechanics without getting dizzy hasn't properly understood it. Quantum computers exploit quantum weirdness to perform tasks too complex for classical computers, because a quantum bit or qubit can register both 0 and 1 at the same time. A classical bit can register only one or the other. A quantum computer can perform millions of computations simultaneously. Quantum computers process this information stored on individual atoms, electrons, and photons. A quantum computer is a democracy of information. Every atom, electron, and photons participate equally in registering and processing information. And this fundamental democracy of information is not confined to quantum computers. All physical systems are at bottom quantum mechanical, and all physical systems register and process information. The world is composed of elementary particles, electrons, photons, quarks, and each elementary piece of a physical system registers a chunk of information. One particle, one bit. When these pieces interact, they transform and process that information bit by bit. Each collision between elementary particles acts as a simple logical operation, or OP. To understand any physical system in terms of its bits, we need to understand in detail the mechanisms by which each and every piece of that system registers and processes information. If we can understand how a quantum computer does this, then we can understand how a physical system does. The idea of such a computer was proposed in the early 1980s by Paul Benioff, Richard Feynman, David Deutsch, and others. When they were first discussed, quantum computers were a wholly abstract concept. Nobody had a clue how to build them. In the early 1990s, I showed how they could be built using existing experimental techniques. Over the past 10 years, I have worked with some of the world's greatest scientists and engineers to design, build, and operate quantum computers. Excuse me for 1 second. There are a number of good reasons to build quantum computers. The first is that we can. Quantum technologies for manipulating matter at the atomic scale, have undergone remarkable advances in recent years. We now possess lasers stable enough, fabrication techniques accurate enough, and electronics fast enough to perform computations at the atomic scale. The second reason is that we have to, at least if we want to keep building ever faster and more powerful computers. Over the past half-century, the power of computer has doubled every year and a half. This explosion of computer power is known as Moore's law. After Gordon Moore, subsequently the chief executive of Intel, who noted its exponential advance in the 1960s. Moore's law is a law not of nature, but of human ingenuity. Computers have gotten 2 times faster every 18 months because every 18 months engineers have figured out how to halve the size of the wires and logic gates from which they are constructed. Every time the size of the basic components of a computer goes down by a factor of 2, twice as many of them will fit on the same size of chip. The resulting computer is twice as powerful as its predecessor or a year and a half earlier. If you project Moore's law into the future, you find that the size of the wires and logic gates from which computers are constructed should reach the atomic scale in about 40 years. Thus, if Moore's law is to be sustained, we must learn to build computers that operate at the quantum scale. Quantum computers represent the ultimate level of miniaturization. It's the ultimate ephemeralization, doing more with less. The quantum computers my colleagues and I have constructed already attain this goal. Each atom registers a bit, but the quantum computers we can build today are small, not only in size, but also in power. The largest general-purpose quantum computers available at the time of this writing have 7 to 10 quantum bits and can perform thousands of quantum logic operations per second. By contrast, a conventional desktop computer can register trillions of bits and can perform billions of conventional classical logical operations per second. We are already good at making computers with atomic scale components. We are just not good at making big computers with atomic scale components. Since the first quantum computers were constructed a decade ago, however, the numbers of bits they register has doubled almost every 2 years. Even if this exponential rate of progress can be sustained, it will still take 40 years before quantum computers can match the numbers of bits registered by today's classical computers. Quantum computers are a long way from the desktop. This book was published in 2006, 20 years ago. So we have to take that information based on that, and I have no calibrated information to say that when he writes 40 years from now, 20 years ago, are we still on pace for that or not? I do not know. I cannot confirm that. Any question at this moment?
Hi. Yes. Can I go?
Yes, please go ahead.
Okay. The first thing is that I take this, if I take it in light of Kelly's formula, quantum computing is going to be extremely, or is already extremely useful at the level of a focus. Remember Kelly's formula, identify patterns on the numerator and divide by the focus. What are you going to do off? So the ability to compute at the quantum level is going to be magnifying the total results of our investigation. But we need to ally. You cannot just say you are using quantum computing at the expense of classical computing. Classical computing identify the patterns and is very good at that. And quantum computing is going to look at the grain size of the pattern and make differences that are going to be applicable to things that we have to solve in our locals. That's the first thing first comment that I'll make here. The second comment is that I'm already hearing around the thieves that are going to mislead people. When I'm saying misleading people, big money is already aligning for quantum computing to be the next buzz and sucking every other average server into the schemes that will mislead them and jettison their resources. I'm already hearing, like, it's going to be the same thing as we heard with blockchain. It's going to be the same thing as we heard with AI. It's going to be the same thing all over. We really need to build in ourselves that ability to, how will I call it? To identify really the good from the bad, or what is going to mislead us into wasting our energies and the little that I have. If we really want this to empower in the light of helping the maximum of humans, you know, in the direction of progress. Those are the two things that I have, the two comments that I had to make on this.
Thank you. So you're saying human nature never changes, no matter how we compute it.
We have to be
Anything
aware.
else?
Yeah.
Yes. Yeah, in terms of awareness, in the past years, I've heard repeatedly that encryption research was geared towards quantum computing resistant encryption, because with the advent of powerful quantum computers, everything that relies on traditional encryption, basically the entirety of the internet, will be at risk of disclosure to everybody, the nullification of encryption. So the research was geared towards encryption techniques that would be resistant to quantum computer cracking, which is part of awareness, protecting ourselves.
Yeah. But most dangerously is that hedge funds are already out there seeking ways to appropriate them.
Yeah.
They want to appropriate it and put patents and things like that.
Yeah.
So they want to use quantum computing to exploit, the profits that they can extract from the system at the very fine level. And they're already at work, while the big public is still like fearful and not even aware of what's going on.
Yes, I agree with that. Thank you. Anybody else? So we go on to the third reason to build a quantum computer. The third reason to build a quantum computer is that they allow us to understand the way in which the universe registers and processes information. One of the best ways to understand a law of nature is to build and operate a machine that illustrates that law. Often, we build the machine first and the law comes after. The wheel and the top had existed for millennia before the establishment of the law of conservation of angular momentum. The thrown rock preceded Galileo's laws of motion. The prism and the telescope came before Newton's optics. The steam engine preceded James Watt's Governor and Sadi Carnot's second law of thermodynamics. Since quantum mechanics is so hard to grasp, wouldn't it be nice to first build a machine that embodies the laws of quantum mechanics? By playing with that machine, one could acquire a working understanding of quantum mechanics, just as a baby who plays with the top grasps the principle of angular momentum embodied by the toy. Without direct experience of how atoms actually behave, our understanding remains shallow. The toy quantum computers we build today are machines that will allow us to learn more and more about how physical systems register and process information at the quantum mechanical level. Can I ask, what is a top? Just as a baby who plays with a top grasps the principle of angular momentum?
It's the spinning top, Fred. The spinning top.
Okay, that's how it's called. Thank you.
Yeah.
Thank you very much.
Okay.
Anything about that? So we go to the final reason to build a quantum computer is that it's fun. In the pages to come, you'll meet some of the world's foremost scientists and engineers. Jeff Kimball of Caltech, constructor of the world's first photonic quantum logic gate. Dave Wineland of the National Institute of Standards and Technology, who built the first simple quantum computer. Hans Moij of the Delft University of Technology, whose group gave some of the earliest demonstrations of quantum bits in superconducting circuits. David Corey of MIT, who built the first molecular quantum computer and whose quantum analog computers can perform computation that would require a classical computer larger than the universe, that can perform quantum computations that would require a classical computer larger than the universe itself. Once we have seen how quantum computers work, we will be able to put bounds on the computational capacity of the universe. This concludes the reasons to build a quantum computer, which were it's fun, before that, they allow us to understand the way in which the universe registers and processes information. Before that, the other reason, the second reason is that we want to keep building faster and more powerful computers. And the first reason is that we can. We can because we have the technology to do so. So the reasons to build quantum computer were the first reason that we can, the second, we need more powerful computers. Third reason is that they allow us to understand what's going on. And the last reason is because it's fun.
Wow.
Yes, Manu?
Yes, I'm just saying wow, because it embodies
Yes.
the best that we say is that learn by doing.
Yes,
you
exactly.
can do all the theories that you want, because we know that those laws already existed.
Yes,
You have to
and
do
this is
like a baby. Yes, yes.
And this is an extreme validation for you that is always playing with your construction toys and building models and showing us using them to demonstrate things. This is a vindication of your activity.
Yeah, but you say that that's actually the way things have evolved. You say
Yes.
that the artifacts always preceded the generalization, the law, the discovery of the law. And he gave so many examples before.
I think we can still do the language of nature. Shall we get going?
Yeah. We still have 30 minutes and we're not meeting. So
We're here. The language of nature. As it computes, the universe effortlessly spins out intricate and complex structures. To understand how the universe computes, and thus to understand better those complex structures, we must learn how it registers and processes information. That is, we must learn the underlying language of nature. Think of me as a kind of atomic masseur, a professor of quantum mechanical engineering at MIT. My job is to massage electrons, photons, atoms, and molecules into those special states in which they become quantum computers and quantum communication systems. Atoms are tiny but strong, resilient but sensitive. They are easy to talk to. Just hit the table and you've talked to billions upon billions of them. But hard to listen to. I bet you can't tell me what the table had to say beyond thump. They don't care about you. They go about their business doing what they have always done. But if you message them in just the right way and can charm them, they will compute for you. Atoms, yes, Manu, you have something to say?
No.
Okay, thank you. Atoms are not alone in their ability to process information. Photons, particles of light, phonons, particles of sound, quantum dots, artificial atoms, superconducting circuits, all these microscopic systems can register information. And if you speak their language and ask them nicely, they will process that information for you. What language do such systems speak? Like all physical systems, they respond to energy, force, and momentum, to light and sound, to electricity and gravity. Physical systems speak a language whose grammar consists of the laws of physics. Over the last 10 years, we have learned this language well enough to talk to atoms, to convince them to perform computations and report the results. How hard is it to speak to atoms? How hard is it to speak atom? To learn to converse fluently takes a lifetime. I myself am a poor atomic conversationalist. Compared with other scientists and quantum mechanical engineers you will meet in this book, I'm not very good compared to the others. To learn enough to carry on a simple conversation, however, it is not so hard. Like all languages, atom is easier to learn when you're younger. With Paul Penfield, I co-teach a freshman course at MIT called Information and Entropy. The goal of this course, like the goal of this book, is to reveal the fundamental role that information plays in the universe. 50 years ago, MIT freshmen used to arrive full of knowledge about internal combustion engines, gears and levers, drivetrains and pulleys. 25 years ago, they arrived full of knowledge of vacuum tubes, transistors, ham radios, and electronic circuits. Now they arrive chock-a-block full of knowledge about computers, disk drives, fiber optics, bandwidths and music, and image compression code. Their predecessor lived in worlds dominated by mechanical and electrical technologies. Today's freshmen come from a world dominated by information. Their predecessors already knew lots about force and energy, voltage and charge. Today's freshmen already know lots about bits and bytes. The freshmen in our course already know so much about information technology that we can teach them subjects, including quantum computation, that previously could be taught only to graduate students. My senior colleagues in the mechanical engineers department complain that the incoming freshmen have never used a screwdriver. This isn't true. Fully half of them have used a screwdriver to install more memory in their computers. As part of a research project supported by the National Science Foundation, I have developed a class to teach first and second graders about how information is processed at the microscopic scale. 6 and 7 years old these days also come equipped with scarily extensive knowledge of computers. They too seem to have no trouble learning about bits and bytes when asked to play a game in which each student represents an atom in a quantum computer. They do so readily and accurately. Those of us who grew up before the current information processing revolution, though, have no less appreciation for the variety and significance of information that do our bit-saturated juniors. Old and young, by the time you finish reading this book, you will know how to ask atoms to perform simple calculations, employing machines that are available throughout the world, along with the grammar of the language of nature. Isn't that interesting, Anne?
Yeah, very, very. I already wrote in my book. I loved it. I love that phrase, language of nature. I love it.
Yes,
Mm.
absolutely. Where is it, the language of nature? The language of nature.
Yep.
Here we are. We've joined you for your exit.
I'm sorry?
I say we've joined you for the exit and takeaways.
Hi, Lee.
Okay, you're the boss.
Hi.
So
No, you're the boss. You've done such a great job. We'll just be participants in our how we're feeling and takeaways. And I'll be glad to start, I suppose.
I think we're going to do that now because we just finished an important block of paragraphs, and information processing revolutions will keep us in the same chapter. And I think it's important to make this link and get a reminder of what's been said next week when we move along. So, are you both together? I'm going to stop sharing.
Yeah, we're in the car here.
We're in the car.
Are you on the back seat or the front seat?
We're in the back seat. Oh.
No, we're not in the back seat.
We were in the back seat. Now we moved up to the front just so it wouldn't be so incriminating.
Okay, so Lee, tell us what's going on here and how you're feeling.
I'm feeling wonderful. I read that portion that you went through with everyone, and I understood it. And it was great. And the whole way up from Provo, we watched Jupiter and Venus in the sky. And it was wonderful seeing that portion of our universe in the sky. I'm excited to read more. And I want the ending. I want to know everything at the end. That's what was told to me. Richard, what would you, how do you feel? And what is your takeaway tonight?
Thank you, Lee. I'm feeling like a beginner, and I'm feeling the context of the reading that talked about how long it took to sort of understand and build this kind of computational system and understanding. So I really feel that I'm on page one as a beginner, and needing to digest as much as I can as we move through our readings from week to week. Yeah, so it's sitting in to use the analogy, in the back seat, but by myself to take in and compute the awareness and understanding of our readings. So, Anne, how are you feeling, and what's your takeaway today?
Yeah, I'm quite stoked that we started. We chose this book, and I knew the minute somebody, who was it who recommended it? As long as somebody from our
Fred.
Okay, I knew that as long as somebody in our team here, our group here, suggested, I knew it was going to be a great book, right? However, what it did was, subconsciously, computer technology, digital, all this digital stuff. For me, it was like as far from nature as you can get. So it felt like it belonged in in another world of technology that's very, very it's not based on life, right? But this book has just done that. It just linked it, and now the whole computing and the whole world of that world of the digital side has just become part of the world and the nature that we live in. And I think just by that first, like this introductory chapter and the prologue alone, has already opened up. And I think for the first time, I'll understand the computers, and how they actually work, just because he's sharing with us how it started, and it jumped so quickly to quantum computers and computation that it like shrinks the whole journey of the whole development and evolution of computers into like just a couple of pages. Yeah, and the other thing I'm going to look into is also I've got Richard Feynman's book downstairs. I just never got around to reading beyond chapter 1, I think. So I'm going to go have a look at it again. And the last bit is, Steve, you get very excited about angular momentum. And this book, when it linked to a top, and I said, oh, okay, I can deal with a top. So now angular momentum seems a little closer than it was before. Yeah, just so you know. And Fred, thank you so much for taking on from Steve today. Steve, I don't know how you do this for so many years. Okay, all right, thank you. And Manu, how do you feel, and what is your takeaway today?
Your microphone, Manu.
You muted me.
Lee and Steve, I envy you. Like your colorful things, and in the car, I don't know where you are going, but I envy you. But what is this? I'm left here with a question. What is this? It was called a lemon, huh?
A lemon?
Yeah, it was called a lemon. Is it still a lemon?
Oh, yeah. It's a half a lemon now, I see. The other half I can't see.
Where is the information?
Yeah.
Good. Lemonade.
I think that's what I've learned during the course of this introduction.
Become bits.
Yep.
So thank you. Is it to Steve or to Fred? Okay, Steve. What shape are you, my friend? I can see your shape already. You don't need to tell us the shape. So what do you take?
I was in a different shape when I was in the back seat of the car. Now I'm in the front seat of the car. I'm a little different shape. We're more no. Hey, I've been very excited about this book because I knew that I had this family event tonight. I didn't think it would take this long. I thought I'd be in the car in 15 minutes, and then I'd be home in 40 minutes, and I'd finish the last hour of the call. Lee and I would with you. But the event took longer, and family's a wonderful thing. And what's cool about today is I got to participate with my family and my family. I got with my daughter and with you guys, and I appreciate that very much. And in preparation for tonight, with Lee, we read the introduction. We read the acknowledgement, in fact, and we read this first chapter. We didn't get as far as we read tonight because we didn't do the information part, that last section, which I'm grateful that we did. And it just seems to me that the introduction, the whole concept of the apple, is just a profound metaphor to know how, I love the way he said that the apple was in the Garden of Eden and it represents the knowledge of good and evil, right? And then he goes to Newton and the thing. But what he didn't talk about was the fact that the apple is in a perfect torus. It's in the shape of a torus, which is what it would. It's the shape of a tetrahedron or a double tetrahedron. It's the shape of energy, and we've been studying Fuller with synergetics and then Fuller explanation, trying to explain energetics to me, synergetics to me, and then we've studied cosmology. Everything's talking about vibration, and I will say that this conversation about this quantum reality, this idea, information theory and quantum computing, I really think that I'm very prejudiced about what I'm hearing us read because of Stephen Wolfram. If you guys can, you should go out and listen to Stephen Wolfram's TED Talk. And he talks about his automata. He talks about two-dimensional computational theory. But then he's in Wolfram language and the other things he's done, he's got into multiple dimensions, 3 and 4 dimensions of this computational idea that the universe is simply computation. And I'm using that context to say, okay, let me start from the foundation and get these building blocks. And I hope that that Mr. Lloyd here, Dr. Lloyd, I hope his promise that at the end of the book, I'm going to know how to build a molecular quantum computer. I'm going to be pissed off if I can't. No, I'm very excited. And let me tell you the one big takeaway for me as I read through this. The nature of the universe is democratic.
Mm-hmm. I got that.
Maybe it's not, maybe democratic could be the right, he says democratic. I think it could be consensual or more Bohmian. In other words, every bit of information affects every other bit of information in some way, leading to the complexity we have here today. And yet, that's the nature of the universe, is that everyone counts. Everything counts. And wow, I'm really looking forward to this book. I'm going to go back. I think his introductory section there, where he talks about his speech with the apple, that would be worth memorizing, because I could just talk about an apple, and people think I'm a genius when it comes to information theory. So I'm going to rip that off for sure. And Fred, as far as I love the fact that you're hosting this exploration. The way you went back and said, okay, in the last couple of chapters, here are the 4 key points. And I really like that. I'm going to go back and read through and have some key points too. This is an important book. And one of the things that I really loved about his 4 reasons to build a quantum computer, the 4th reason is it's fun. Wow, do I like that. If I can't get up in the morning and feel like I've got something fun to do, why get up in the morning? And what could be more fun than building a molecular quantum computer? So let's go for it. I'm all excited. Okay, Fred, thank you for putting up with my administrative mishaps and for presenting this book, Programming the Universe, and for conducting the reading. You did a great job as I listened, and I'm looking forward to further conversation. Fred, how are you feeling, and what are your takeaways tonight?
Thank you, Steve. Thank you, everybody, for liking the book. I like it too. I believe after the response you all gave that we're going to learn a lot of things, all of us, and we're really going to enjoy it along the way. I think even though we labeled it the more technical book of all, I think it's written in a way that's going to make it pleasant to learn something from it.
Yes.
And it's not, I mean, there's some math into it, but it's not deeply rooted in math. We can maybe gloss over it and still get the important points. But this introduction really is pleasantly written. It's fluid. It's easy to understand. We go through it. Everybody got some insights, some ideas, some links to the previous books, previous learnings, like Anne and Manu, and Richard likes it too. So if Richard likes it, it's a win. It's So thank you all for the response you gave me. Somehow it was a little bit there was a little bit of apprehension on my part. Say, okay, how is that going to go with the group? Because it's one thing to get the book you proposed acknowledged by everybody. It's another thing that you all like it, and so I'm enjoying that. So yes, and I'm done. And it's 55, so. We lost 25 minutes in the meantime. We started on time and we're 5 minutes early, and yet we learned a lot. So that's pretty good.
Good.
Anybody else has something to say before we go?
All good.
All good.
Good.
Thank you very
I am
much.
great. Thank you all.
Thank you. See you on Wednesday.
See you all
Bye-bye.
Wednesday.
Yes.
Yes. All right. Bye-bye.
Bye.
Bye-bye.